All right, why don't we move on to the agenda here, Tanya? All right, so in this session, we'll talk about where capital fits into the overall Xcelerator portfolio and provides a model-based design environment. And then we'll focus in on three important integrations into that Xcelerator environment, to Teamcenter, to NX, and to Polarion. So let's go ahead and get started. All right, so kind of across a broad range of industries, the consumer demands for more functionality are driving the electrical and software content to just levels we've never seen before. And that electrification of those products is driving the need for tighter integration between the engineering disciplines, where MCAD once dominated and electrical and software was kind of an afterthought. Now we need to bring this digital twin together, and that brings the full scope of the products together in this virtual model-based environment. And that's really what's at the heart of the whole Siemens Xcelerator portfolio. So, to realize that digital twin, it's just imperative that we diminish those boundaries between these different disciplines, between mechanical, electronic, electrical, network, software, simulation, all of these different environments we have, and we just need to, we have walls right now that impede the successful productivity and innovation. So, correctly executed on, we can remove those interdependencies, we can understand the handoffs between those domains, we can establish traceability between these domains, and we can flow the data between and actually get to a product in the end that we can certify and know it did what it's supposed to do. So the Xcelerator portfolio kind of provides this best-in-class set of tools and methods for defining that digital twin, taking it all the way from a concept through design, through integration and manufacturing of the end product. And Capital is the suite of tools that provides the EE systems environment portion of the Xcelerator portfolio. It's integrated into the overall Xcelerator environment to provide a broad solution to our customers. So, at a high level, in EE systems development, there's kind of three main areas you can divide it into. And on the first stage, the system architecture on the left there is kind of refined from early modeling inputs, enhanced with additional data and artifacts needed to optimize the EE design proposals, and then feed downstream into two tracks, one implementing the electrical interconnect system, and the other implementing the software functions and associated networks. So, we have a number of focused solution areas that then refine those proposals out of the architecture during detailed domain-specific implementation flows that take their domain-specific data and really take it to the next level of design. And then in the bottom part of that flow is where the electrical distribution system is designed both logically and physically, verified by construction methods, and prepared for manufacturing. And then the manufacturing of electrical harness is a hugely complex operation, and Capital provides solutions that optimize that process. And then following the entry of those products into service, customers need to be able to efficiently service, diagnose, repair electrical systems, and Capital provides solutions that make that process more efficient than is typically possible without advanced tools. So Capital itself is a data-centric system built on data and process backbones that enable extremely high levels of automation, data coherency, and integration with the adjacent domains. And this EE data management system enables traceability, change management, configuration management, and it is an environment that our customers have demanded and that we've built up over a number of years to satisfy those demands. But the EE systems are a part of the wider program lifecycle within organizations, and we do provide deep integrations into PLM systems and other necessary domains throughout the product development process. So with that exploding complexity of the EE systems, development happens in the context of this model-based engineering. And that's what Capital is all about, is model-based engineering, not just model-based systems engineering, model-based throughout the design process. So to deliver this, this whole integrated system, we integrate with other domains to really deliver that integrated system development environment into MCAD, PLM, and ALM systems. And in today's session, we'll take a deeper look at 3 of those key integrations from Capital into the overall Xcelerator solution. So let's start with Teamcenter and how this integration enables the EE data to be integrated into the overall product structure. So EE design is just one aspect of that overall product design. So in the context of the Xcelerator portfolio, it must integrate seamlessly into that overall product structure that's held in Teamcenter. And Siemens open architecture enables this integration, allows the data needed by all of those engineering disciplines to be mastered in Teamcenter, consistently used across all areas needing it, and basically ensures that the products designed and implemented are based on a common understanding of the requirements, the features, the variability and configuration of the larger context, as well as providing an overall status of the various pieces that make up that product. So as I said before in introducing Capital, Capital itself has a rich set of data management process control capabilities, and it allows us to be deployed into customers not using other PLM systems or not connecting EE to their existing PLM. But when we're in the context of a Teamcenter environment and a customer that's using Teamcenter, Teamcenter takes control over many of those lifecycle responsibilities, and Capital kind of pulls back and is used to concentrate on providing that EE design environment at which it excels. So in such a setup, Teamcenter is responsible for the lifecycle and approval process of both the components, parts used in the EE designs, as well as the designs themselves. The release and approval process implemented via standard workflows in Teamcenter to ensure consistency with the overall product development lifecycle. And Teamcenter also holds information that's relevant to multiple design disciplines, and Capital will merely use that data to drive the EE design and ensure we have consistency across the domains. So one of the key aspects of Capital's integration into Teamcenter is the use of active workspace embedded directly in the design applications to provide direct in-tool access to the overall product information and to the data published to Teamcenter, not just by Capital, but by other domains working on the design of the overall platform. So Capital is able to add integration and application-specific icons directly in the active workspace frame in order to provide context-sensitive access to the integration features. And we'll see how these are used later in the presentation to provide a seamless integration experience. So with those foundations set, this slide provides an overview of the various integration touchpoints that are currently available in the released software. So we'll describe each of these in a little bit more detail over the next few slides here to ensure you have a fundamental understanding of the capabilities and how they provide value to that overall design process. So let's start at the beginning of the product development process with a definition of models representing system behavior. So in order to provide an initial electrical systems design, we have the ability to take a managed system modeling workbench design from Teamcenter and directly read that into Capital systems at the front end left side of that flow. And this really allows customers to reuse their functional or system definition from a systems model to be in the initial EE design. And then that initial design includes all of the relevant system elements, connectors, and associations to Teamcenter requirements for the EE engineer to design their system. And then once complete, that EE engineer can publish the refined Capital design to Teamcenter and also capture that traceability to the original system and system design. So this allows anyone in Teamcenter to visualize the full traceability of all of those connected artifacts. So system modeling workbench is that first integration. And then if you move on to the next piece of this would be kind of managing the association of the requirements in Teamcenter with the relevant objects, implementing those requirements in Capital. In the case of the system modeling workbench, any requirements associated to the system modeling workbench objects are automatically carried forward and linked to the resulting objects in Capital. However, even without using the system modeling workbench, users in Capital are able to use the embedded active workspace to navigate to the relevant Teamcenter requirements and establish links between the two. And a little later, we'll take a look at what that looks like, but actually in the context of Polarion. But from within the Capital, from within the Teamcenter environment, even when you're not connected to Capital, a user can select the linked objects and bring up a web-based view of the Capital data and highlight exactly where those requirements are linked. So, so you can come through Teamcenter and understand the full breadth of the objects that are implementing those requirements. And then those associations can be used to validate all of the requirements associated with their EE implementation have been fulfilled. Another area where Teamcenter holds the overall product information that's needed in the electrical design process is in the area of configurability. Teamcenter's product configurator is used to define the optional content in the platform, as well as the relationships between those options, such as inclusive or exclusive relationships. So for example, a mandatory and exclusive relationship between the engines could be available. There are multiple choices for an engine, but you can only have one, and you must have one in your car. So the integration of product configurator allows these options and their relationships to be mastered in Teamcenter and used to populate the Capital version of that model into the product plan in Capital. And then that data can be used to calculate the optional set of configurations needed to cover all the electrical and mechanical variations. And then using that powerful automation features in Capital, we arrive at an optimal set of manufacturable harness parts. So the next area of this integration that we'll highlight is component libraries. So although Capital has a robust environment for entering component data with all relevant electrical information to drive the electrical design process and automation, the identity of a component across all applications using Teamcenter, as well as the life cycle of that component, is owned by Teamcenter. And so therefore the challenge is to ensure that the Capital uses the same identity for the component as Teamcenter, so it can be correctly represented and included in the bill of materials. So to achieve this, there are both interactive and automated ways to establish that link. The interactive association and synchronization achieved by embedding the active workspace actually into our Capital library application. And that gives the librarians in Capital the ability to navigate to the relevant components in Teamcenter, either initially establish the relationship or to update the Capital component attributes based on the latest data held in Teamcenter. And the use of the active workspace here also allows those Capital librarians the ability to see all other aspects of that part held in Teamcenter, not just the electrical aspects of it. So, so they can get over there. But kind of to ensure those libraries are always in sync without manual intervention, the EDA library capability in Teamcenter is used to extract the updated components and automatically send them to Capital. And so the schedule for that integration is defined on the Capital side using our Capital Enterprise Assets application, and it initiates the pull of the latest component information from Teamcenter and manages the merging of that data over into the Capital library itself. So with those links established to the component library and the Capital data model populated with the relevant cross-domain information, electrical designers can use the powerful automation, electrical design features in Capital to complete the designs and publish those results back into Teamcenter. And there are a set of standard item and data set types for electrical that are shipped with Teamcenter that customers can quickly configure. The default configuration in Capital uses those item and data set types when we publish to Teamcenter. And this is what we use for Teamcenter X deployment is out-of-the-box data set types defined in Teamcenter. Out of the box, Capital ships with those same data types. So for a new customer, it's all good. However, many customers already have these item types and data set types defined and in use. So we provide the ability to configure the integration to publish to any design type in Teamcenter as required. And that configurability is key to enabling the Capital integration into any new or existing customer setup. So by default, Capital will publish a zip file of design XML representing the design for archival purposes, as well as a graphical representation, PDF by default. Others are supported. However, customers can configure that integration to publish any report available within Capital, as well as having full plug-in capabilities to allow any type of data to be published along with the design itself. So in addition to the design content, a full bill of materials from a Harness XC or harness designs can also be published into the Teamcenter BOM structure under the item. And this is where the link to the component in Teamcenter becomes extremely important, as the BOM line in Teamcenter has to reference a Teamcenter item. So we have to establish that link to the component so that when we publish the BOM, it all hangs together. So this integration has multiple plug-in points where custom logic can be inserted into the process to ensure the state of the data is as required. You can stop the publish if those conditions aren't met. And I'd say, it's just suffice it to say in this area, there's a lot of choices to be made in how and what the integration publishes, and there's extensive documentation out there around configuring the integration to any particular customer's needs. So now let's move on and talk about the life cycle of Capital designs in Capital and how they can be controlled via what we call the Teamcenter driven design process. So in this flow, the creation and revisioning of electrical designs is initiated from Teamcenter to establish the existence and identity of an electrical design. So from within the embedded active workspace in a Capital design application, the engineer can navigate to an item in Teamcenter and create the Capital design that will implement that item and implement the required electrical connectivity, and eventually then publish the results of that design activity back to Teamcenter, as we talked about in the previous slide. So this context-sensitive integration is achieved with additional Capital capabilities added to the embedded active workspace. And this allows users to create new designs in Capital from existing Teamcenter items, or associate an existing Capital design to an existing Teamcenter item. And then after that association is made, push any attribute changes from Teamcenter back onto the Capital design. So this is a process favored by many of our customers to ensure that their electrical designs are fully integrated into that overall product and really drive everything from Teamcenter. And carrying on to that theme of Teamcenter managing the life cycle of Capital designs, the integration also supports the use of workflows in Teamcenter. And currently there's two types of electrical workflows available with example workflows that are shipped directly with Teamcenter. So the electrical design review workflow allows a Teamcenter user to progress a Capital design through an approval process and ensures the design and Capital follows the Teamcenter states to keep the release level on the Capital design in sync with the changes being made in Teamcenter. So that workflow also supports rejecting the approval and moving the capital design back to a state of in work so issues can be fixed, and then the design can be republished and resubmitted to that workflow. The second workflow is the electrical design revise workflow, and that's usually used for change management. And that allows a Teamcenter user to create a revision of the capital design ready to have either new functionality or a defect fix to be implemented. The capital user simply opens the target revision after the workflow is completed and starts his work. But in order to enforce process, capital has the ability to set a preference that actually forces all design creation and revisioning to be driven through Teamcenter. And as a final piece of that capital Teamcenter integration, Teamcenter can be used to mediate the exchange of data between capital and NX. So instead of using kind of uncontrolled methods of file exchange, the operating system or email, the data can go directly into Teamcenter, where either application can access it in a configuration controlled way, ensuring the right files are being used from the right revisions of both sides. So when capital is connected to Teamcenter and the data is bridged out, it'll automatically be placed into Teamcenter instead of to the file system and under the item that we're publishing. And then in the embedded active workspace, you can use to navigate and bring data from NX directly back in to capital. So hopefully you've seen here, the capital integration with Teamcenter has many touch points to enable that digital thread to be created, maintained, and leveraged to integrate the electrical data into that overall product structure. So at this point, I'd like to hand the presentation over to Tanya, and she'll take us through the NX related integrations.
Thank you, Glenn. Moving on now to the topic of integrating electrical and mechanical design processes. Let's discuss how NX capital integration strengthens the Xcelerator offering around electrical design. Just as there are benefits to be gained by integrating electrical data into Teamcenter, there are also benefits to breaking down the silos between mechanical and electrical design. As you see here in the results of an engineering.com research report, 72% of teams say an integrated electrical and mechanical design environment can significantly reduce product delivery time. Why is that? In many companies today, electrical and mechanical design teams work separately, and therefore the integration done is late in the design process. This results in either rework to the physical structure of the platform that can be very costly, or more likely a suboptimal integration of the wiring, which results in some of the electrical characteristics not being accounted for in the initial design. In either case, there is an impact to schedule and quality. So it is essential to obtain seamless integration, enabling ECAD, MCAD co-design across Xcelerator portfolio. In most design flows, engineers are typically working concurrently on designing the physical harnesses in NX, and electrical connectivity is being defined and designed within Capital. So NX is responsible for defining the physical geometry of the harness, the fixtures and fittings, and ensuring that there is sufficient space in the vehicle for the harness to be routed and fitted. Whereas Capital is responsible for mastering the electrical connectivity and subsequently fully defining the harness as an electromechanical product. The NX and Capital electrical data are then combined to make manufacturable harnesses. So the collaboration between these two tools is key to enabling a precise concurrent design. Capital Tools has many touch points with NX across all domains like Capital Logic, Topology and Integrator, and Harness XC or Modular XC. Capital provides a robust and flexible set of integration capabilities to enable the digital thread to be created, maintained, and leveraged to integrate electrical data. With Capital Logic, we have the ability to send wires to NX and have them routed and wireless returned. In the topological tools, we can import the bundle topology and have routed or synthesized wiring. We can then calculate bundle diameters and splice positions and return them back to NX. And finally, with Capital Harness XC and Modular XC, we can pull the full mechanical description of the harness parts, including bundle protections and supports, and have the wiring synchronized. We can then calculate bundle diameters and splice positions and return them back to NX. So this process also eliminates the need to have any wiring in MCAD tool if desired. This separation of data means that an NX harness will not need to be modified and rechecked whenever low-level electrical changes happen. So this reduces the overall number of design change approvals that are needed to implement a change and improves the overall design time. So all these integration capabilities are enabled via a combination of our bridges framework and adapters, which handle the exchange of information between NX and Capital. In the left, we have a set of plugins using MCAD applications APIs, and they are deployed within the MCAD tools. We have bridges framework with its adapters that are able to understand what comes out of the MCAD products. And then we have our patented flattener that is able to transform between 3D representation from the MCAD product to the 2D representation we require. And finally, we have change manager that is able to understand the difference between received set of data and what's already in the design. So the goal of these integrations is to ensure that key data shared between electrical and mechanical designers is aligned early in the design process and stays aligned as development continues. In order to address this, electrical and mechanical designers need to exchange data as early as possible and then iterate as there will be outside forces driving change in both areas. So change management is a fundamental backbone to this ECAD MCAD integrations. We'll look at it in more detail in the later slides. The extended wiring and harness data integration is supported between Capital and NX now, enabling world-class integrations with NX compared to integration with non-Siemens MCAD tools. This extended integration enables CAD zip file exchange, the format being PLM XML and JSON file contained in a zip. By adding JSON file to the data exchange process, we are able to integrate new capabilities like unfolding flattener, connector and backshell clocking, and NX specific 3D flattening plane. And during bridge out, this format enables NX stock diameter updates and automatic splice positioning. So there are multiple ways to accomplish the integration depending on organizational requirements. We have file-based mode, connect mode, direct Capital navigator mode, and Teamcenter mediated MCAD collaboration mode. In connect mode, we can directly connect the electrical application to NX to exchange data and understand the electrical routing in the physical context by cross-selecting between the two tools. In Capital Navigator mode, user is able to access Capital data right within NX without having access to a separate Capital installation. And another method of integration is to use Teamcenter to hold the files to be exchanged and the embedded active workspace in the Capital application to navigate to the desired version. This provides a structured file-based exchange as opposed to a pure file-based exchange where there is no guarantee on the source or the version of the file being imported. Moving on, let's see how Siemens Xcelerator portfolio aids in the ECAD MCAD core design process. This is the first use case in NX Capital integration flow. The basic idea here is that Capital is the master of electrical content and NX takes care of 3D harness models. The ECAD designer begins by creating the wiring and connectivity layout in Capital. This layout includes key components such as wires, connectors, multicores, and splices. The designer then exports this wiring data to the mechanical engineer. The mechanical engineer imports this data and NX automatically links the electrical data to the 3D objects. Then we can route the wiring through the platform, enabling bundling diameter calculations to take place. When ready, a file containing these incremental changes is exported for review by the ECAD designer. The ECAD designer then imports this data and performs a number of checks on the design. The designer can use the 3D wire length from NX to perform voltage drop calculations and ensure that enough space has been reserved in the mechanical design to fit the wiring bundle. Changes can be made as needed, and a new incremental file can be sent back to the mechanical engineer. And this flow can be achieved either by connect mode or file-based mode. And this wiring exchange use case that we have just seen can also be achieved by direct Capital Navigator integration. This mode allows MCAD user to access ECAD information without having access to Capital application. In the previous integration scenarios we have looked at, the integration was achieved either in disconnected or connected mode. The disconnected mode relies on the exchange of an intermediate file to bring capital data into the MCAD application, while the connected mode doesn't require an intermediate file but still requires access to a running application. In both cases, MCAD user has to switch between NX and Capital to exchange data. Now within Capital Navigator, the user is able to access Capital data right from within NX, removing the need to have access to Capital installation or even knowledge of using the Capital tool. This is a key to enabling collaboration and co-design between ECAD and MCAD domains and strengthens the digital continuity through the product design phases. The steps in this flow are the first, wiring data is read from Capital by selecting the appropriate harness filter, and then connectors are assigned in NX and wires are automatically routed. And the next use case is harness exchange between Capital and NX. Harness description from NX, including bundles, supports, and protections, are imported into Harness XC via Change Manager. Change Manager is used to control the incoming data. Then harness is flattened as desired and processed into harness design. Wires are not present in this harness design because of change policy settings. So harness is synchronized with Capital wiring design to get wiring information. And then bundle diameters are calculated using the synchronized wiring and splice optimization can be done. So these new bundle diameters and updated splice positions are exported back to NX. So in the same way as before, the bundle diameters and splice positions in NX can also be updated by NX Designer using embedded Capital Navigator. In many companies, NX has been used as the container for electrical data, even though it is not an electrical design tool. This can cause excessive design sizes as the wiring connection data has to be fully implemented and saved in the NX model. In some cases, this leads the companies to split the harness across zones to manage the data sizes. To address this issue, we have introduced the ability for NX to contain only the harness structure and connectors and to visualize the wires defined in the electrical model in the context of the NX harness. This allows NX user to see the wire routes and evaluate splice locations in the context of the 3D model to ensure that they'll correctly integrate. In addition, to facilitate clearance checks and other analysis, the bundle diameters calculated in the electrical data can be applied to the NX model so that accurate bundle diameters are shown. This flow is also possible in connect mode or file-based mode. So as you see here, after all the harness engineering tasks are done within Capital, MCAD engineer can get the latest design data within the NX application. The user can apply Capital context to his NX electrical assembly, enabling automatic splice creation and positioning, and bundle diameter updates in NX based on wiring content. So a key element in realizing these integration capabilities across multiple domains is powerful change management. Clear ownership of various types of data must be established and can then be captured in digital form to define the rules of exchange. With these rules in place, a designer in Capital can proceed with adding detail to a model whose physical structure is defined in MCAD without fear of that work being lost at any integration point. So bridging in of design data into Harness XC or Integrator is enabled through the Change Manager, which is a preview, validation, and change control interface that allows linking harness objects with externally sourced entities, as well as synchronization of changes in shared data subject to a change policy if required. The Change Manager facility enables you to link bundles from your Capital design with their corresponding bundles from the external source. When you link a bundle from annex design with a bundle from the capital existing design, the properties for which the master source is the capital application remain on the object in capital, and the object properties for which the master source is the external application, for example, length, they'll be overwritten by the value from the external harness data. So change policies allow you to control the way in which changes are to be propagated during harness synchronization and bridging processes. They can also regulate which objects are permitted or prohibited from being created, updated, or deleted. For example, when we are bridging in NX topology data and we do not want to get wires from NX, we can create a change policy to not create, update, or delete wires. And when this change policy is used during import, wires will not be updated based on the incoming data. Here is an example that demonstrates how powerful a capital's change manager is in handling data changes. We begin by adding an installation to an existing bundle in harness XC, and then we change the bundle structure in NX. Here the goal is to propagate the change in bundle structure in harness to harness XC without deleting the installation that is added in XC. So now we are changing the bundle topology within NX. The wires are automatically routed. In Change Manager, you can flatten the harness as desired, and it also shows preview of incoming data and all the changes that will happen if the external data is processed. So, and when we import the new data, modified data from NX, you see the change in bundle topology in the preview window, but not within the harness XC design. And then we have a change policy to not create, update, or delete any installations based on incoming data. So this change policy is used during import. Once the harness is processed, you'll see that the topology change is reflected in XC, but the installation data is retained. And as seen in the previous video, we have various ways of flattening the incoming 3D harness topology. Orthogonal flattening is the standard style of harness diagram for engineering. It projects 3D coordinates of a harness model onto a 2D plane while laying out the branches perpendicular to each other. And then we have 3D flattening that keeps the 3D representation of the harness as close as possible to the original 3D layout. This closely matches the NX harness shape and many times used in the topology or integrated plane to retain a realistic representation of the harness. And we have unfolding flattener that straightens all bundles while recording the rotational displacements used during the flattening. This allows the clocking of connector keyways and of backshells to be preserved. Backshell and connector clocking angles are needed to achieve the desired installation shape and can only be defined by MCAD. So representation of these angles on harness drawings is crucial for harness fabrication. We now have NX extended integrations to support connector and backshell clocking. In 2D harness drawings, the clocking angles are computed with respect to the flattening plane and visualized on the connector using styling capabilities. The clocking computation is done with either unfolding flattening or orthogonal flattening methods. When orthogonal flattening is used, the harness is still unfolded using the unfolding algorithm to track clocking angles, but then laid out using the orthogonal pattern. Finally, I'd like to highlight the importance of ECAD-MCAD collaboration. It enables co-design across multiple domains and is a driving factor to achieve productivity and design quality. This role is seen key for industries facing a rapidly evolving future. Blurring boundaries across engineering, manufacturing, and service is crucial to improve quality, accelerate product development, and optimize the process over the life cycle. Thank you.
All right, thanks, Chaitanya. Let's wrap this up with capital integrations into Polarion for requirements management. So Similar to the Teamcenter integration using the embedded active workspace, the Polarion browser is embedded directly into our design tools and provides an integrated experience for the designers, allowing the user to browse for requirements or work items. And then from a Polarion work item revision, the integration automatically enables the linking capability. So the link action requires a capital design to be opened, and then on invocation, capital provides an environment where the user can manage and select the capital objects that are the targets where that work item link needs to be created. So what item in capital is implementing that requirement? And the link action is available for all work item types which are configured in the Polarion properties. We've talked about requirements management here, but it's actually any type of work item can be configured to be linked. The user just selects the objects in the capital design for that association and then proceeds with the link creation in capital. And then in the capital links tab, you'll see there in the browser, it lists out all of the established links and enables you to visualize the capital design with hyperlinks and filtering capability. So that link tab also provides the actions to manage and update those links. So the view requirement action will automatically open an external Polarion browser, locate and open the selected requirement revision, and then in the hyperlink section of the Polarion, you can inspect on the Polarion side the bidirectional storage and linking to the capital objects. But during development activity in capital, there might be the need to change the associations to the design objects that are implementing that requirement. So the edit association action also allows you to adjust and reassign the design objects and then automatically update the requirement on the Polarion side. And then capital commands like export, import, revise of a design will create new design revisions, and the requirement links can be forwarded and taken forward into those new designs in capital. And that reconcile requirements action ensures that the links available in capital design are reflected on the Polarion side to ensure that correct bidirectional linking. Removal of requirements on the capital side will also automatically update the Polarion requirement and reflect that change. So that bidirectional linking enables the Polarion user just completely outside of a capital environment to view the associated capital object. So on the stored relation in Polarion, the available hyperlink will automatically view the data using our Capital Enterprise Reporter application, web-based application reporting. All right, so those are kind of the three key integrations, and I'd just kind of like to recap here on the items we covered, right? Capital itself has a very rich electrical data management and is a model-based design environment, and enables that digital thread. That the integration into Teamcenter really allows the EE to participate in that overall product structure, and then those integrations with NX kind of break down the silos between those electrical and mechanical designs and really achieve this integrated design process. So I think taken together, these capabilities really enable our customers' ability to realize a model-based enterprise, not just model-based systems engineering, but model-based engineering across the enterprise, and to implement that digital twin. And that really is what makes Xcelerator the leading solution in the market.